Welcome to the first video in our new unit. This is the reactions unit. In this unit, we're going to learn everything we need to know about chemical equations. We're going to learn here in the first one about the symbols that are used in chemical equations, and then we're going to write our skeleton equations, which is when we turn everything from words back into those symbols. Eventually, we're going to learn how to balance these equations, and then we're going to learn how to tell the different types of reactions. And then finally, at the end of this unit, we'll be able to predict our own products. But first things first, let's learn the symbols that are commonly used in writing chemical reactions. The first one is the yield sign. This will be in every reaction that you ever write, and what it means is just to turn from reactants into products. So the arrow points toward the products because that is the new part. That's what the chemical change is going to show you. Now, sometimes chemical reactions only go one direction. Like when you burn gasoline, it forms CO2 and water, and it's pretty much over. But there are some reactions that go backwards, and that happens, we'll learn in AP chemistry, as the products accumulate, they actually would start reacting together to reform the original reactants. Those are called reversible reactions, and to show those we use the double arrow, or you might see me sometimes write it in class just kind of like this. We're not going to see that in pre-AP unless I just do something very specific, so that's more of an AP thing. But then we do want to get used to writing states of matter. I think that's very important. It's often overlooked when students are asked to write chemical equations because students have a little bit of trepidation about what state of matter to use, but we're going to learn this, and you're going to get comfortable with it. If one of your reactants or products is a solid, we're simply going to put a little S in parentheses after, to the right of that substance. So when you see that, that means a solid. In the old days, we've learned that solids can be precipitates. So in those old days, that you would sometimes see a down arrow written to the right of a precipitate when it was formed, and that would indicate that it falls out. That's kind of antiquated, so we're not really going to do that. Instead, we're going to focus on writing a S to indicate our precipitates are being formed. That's S for solid. Same thing for liquids. We're going to write a L. You don't have to write it in this cursive script I have here on the screen. I simply use this script here so that you would know we're talking about an L, whereas if I just typed it, it would look like a 1 or an I. I want you to know it's an L. Okay, so usually on the board I'll write a lowercase cursive L. Nothing too fancy. Aqueous, we're starting to learn aqueous this year. It's very important to let someone know that you're dealing with an aqueous substance. That's a mixture. And for ions, that's very important because ions break up. They become dissociated from the compound or from the lattice when you're dealing with those ionic compounds in solution. And then we have G for gas. All right, in the old days, to indicate that a gas was formed in a chemical reaction, and you might see, as we've learned, bubbles or fizzing, an up arrow would be written to the right of that compound or that element. And that would let you know that it's coming out or up. Again, that's kind of antiquated. We're not really going to be using that. Now, there's lots of different ways to make a reaction progress. We've learned that reactions can be endothermic or exothermic. If it's exothermic, heat is given off. For endothermic reactions, we know that we have to put heat into it to make the reaction go. And that's an important piece of information to communicate to someone. So there's a couple of ways we can do that. We can simply write the word heat above the yield sign, or we can just use more commonly a triangle. I don't know why it's a triangle, but that is and has been the symbol for heat added for quite a long time. So heat is one important thing. Pressure is also an important aspect to consider when you're running a chemical reaction. Some reactions need a very specific pressure. If you do need to run a reaction at a specific pressure, like in this example 2 atmospheres, then you can write that information above the yield sign. If it doesn't matter, it just needs to have some pressure, then you can just write the word pressure above the yield sign. So we're kind of getting the idea here that the yield sign is the place to put a lot of information about the reaction. Temperature, if you need, this is different than heat now, because heat just means like put it on a hot plate and let it go. Temperature, on the other hand, would be like you need to get a reaction at a certain temperature and keep it there. So maybe it needs to take place in an oven that you can set the temperature, or a water bath where it has a set temperature. So whatever temperature it needs to be, then you put that above the yield sign as well. I don't know what happened to my yield sign, but it disappeared. I put it back. And then the final little piece of information here is catalyst. You learned in biology that there are catalysts, enzymes that are there to make reactions go faster. So if you want to use a catalyst, once again, you can put that above a yield sign. Just the word catalyst is fine if it doesn't matter. If it needs to be a very specific catalyst, in this example right here, manganese dioxide is a very common catalyst, you can write the name of the catalyst. If it's a biological reaction and you want to run the reaction in the presence of an enzyme, which is a protein that would speed it up, you can write either the word enzyme or specifically the name of the enzyme, like catalase, for example. But again, any information about the reaction that you need to communicate goes above the yield sign. All right, now let's start putting those symbols into skeleton equations. Again, a skeleton equation is just putting everything into symbol forms. It's not balanced, so don't worry about that. We're converting all of our element names into symbols, compound names into symbols. So to do this, you have to recall your ionic naming system, your covalent naming system, and maybe even your acid naming. Let's look at example number 1. We have aluminum metal, so we just write aluminum, and we have learned early in semester 1 that aluminum is a solid in metal form, is added to a solution of hydrobromic acid. We've learned how to name acids. Hydrobromic is binary, so bromide plus the H positive, and since it's a solution, we'll put AQ. It forms aluminum bromide and hydrogen gas. Okay, so I'm going to put my yield sign to know that we're in products now. And now I need to write the formula for aluminum bromide. This is ionic. We have to remember that aluminum is +3 and bromide is -1. So the formula will be AlBr3. And then hydrogen gas. We learned earlier this year that hydrogen is one of the diatomics. And so it is H2. If you've forgotten your diatomics, it's very important for this. Remember Brinkelhoff. Kind of give you an acronym to remember the diatomics. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Brinkelhoff. Now, I didn't skip AlBr3 on accident. I did it on purpose because we need to think about what state of matter aluminum bromide is going to be in. It's ionic, and as we've learned, ionic things are normally solids. So this would be a solid unless, as we also have recently learned, it's in a water environment. Aluminum bromide could be soluble, it could dissolve in water, and it would be aqueous. So we need to consider our Cash and Gia solubility rules here if there's a water environment. Let's address that first. I have an acid, and acids have to be in water, so we do have a water environment. So this is a Cash and Gia problem. Is aluminum bromide soluble according to Cash and Gia? Bromide is the H, it's one of the H's, halides. Aluminum is not an exception, so this is soluble according to Cash and Gia, and so therefore it's going to be aqueous. So there is our skeleton equation for number 1. Let's move on to number 2. We're going to have benzene, C6H6. That's not a formula that I would expect you to know yet, nor the state of matter, but it is going to be a liquid. Is burned in oxygen. Okay, so that's plus O2, which is a gas, to produce, to my yield sign. Now, you may be wondering here, should I put a triangle on top of the yield sign to add heat? And the answer is no. Burning and heating are not the same thing. When you burn something, you react it with oxygen, and what you feel, the flame, the heat, all is exothermic. It comes out towards you. Heating is for endothermic. That's when you put something on a hot plate to cook it. You don't see the fire, you don't see or feel the energy coming out towards you from the reactant. It's going into it from the hot plate. So we're going to make carbon dioxide, CO2. I hope all of you know that CO2 is a gas. And then we're also going to make water, which in this case is a liquid. All right, number 3, potassium chlorate decomposes. So there's my verb. Usually where the verb is where your yield sign goes. Potassium chlorate is ionic, so let's think about the charges. +1, chlorate is -1. So this is going to be just KClO3. And that is solid. We're not told anything about this being a solution or with water. We don't know that this is an aqueous environment, so we're going to assume it's not. So solid. It forms potassium chloride, so that's going to be KCl. Again, no water environment here, so this ionic compound would be solid. And then oxygen gas again, which we're learning is O2, not just O. So that's that one. Number 4. Fluorine gas is bubbled up through a solution of barium iodide to produce. All right, so to produce is my yield sign. Fluorine gas is part of Brinkelhoff, so that is a diatomic gas. And we have a solution of barium iodide. Barium iodide is ionic. Barium is +2. Iodide is -1. I hope you remember where I'm getting these charges from. If you don't, come ask me really quick. This is very important for this unit. So the formula would be BaI2, and since it's a solution, it's aqueous. It's going to produce a solution of iodine. Again, iodine is part of Brinkelhoff, so it's diatomic, and it's a solution. And then barium fluoride, BaF2, because I know fluorine is -1. Now here we go with states of matter. BaF2 is ionic, so there's possibly going to be soluble in aqueous. So we have to consider, is this a water environment? The answer is yes, we have aqueous stuff. So now, is it Cashingia soluble? And the answer here is no. Fluorides are not soluble like the rest of the halides. So that's going to be a solid. Number 5, solutions of lithium hydroxide, another ionic compound. Lithium is +1, hydroxide is -1. LiOH, and it's a solution, so aqueous. And sulfuric acid. Okay, sulfuric acid is an oxyacid. It comes from 8, so sulf8 is my ion here. So sulfuric acid will be H2SO4. To form, there's my yield sign. Water, H2O, and then lithium sulfate. Another ionic compound, lithium is +1, sulfate is -2. So that's going to be Li2SO4. Again, ionic. We're in a water environment here. Not only are we aqueous, but I also have water itself here. So according to Cashingia, this is soluble and it will be aqueous. Okay, one more with me. Sodium bicarbonate and acetic acid will form water, carbon dioxide, and a solution of sodium acetate when they react. All right, sodium bicarbonate is another ionic compound. Sodium is +1. Bicarbonate, if you don't remember that one, is HCO3 -1. So we're going to have NaHCO3 aqueous. It really does, this particular one doesn't specify what sodium bicarbonate is. It could be solid. It wouldn't matter. The reaction would still go. So, and this is one where you have a couple of options to get the right answer. And then we have acetic acid, HC2H3O2. Acetic comes from acetate to form water, which is liquid, carbon dioxide, which is gas, and sodium acetate, NaC2H3O2. And there we have it. Now in these 6 skeleton equations, they're not balanced. So if you're looking at this trying to see, is it even possible, are we violating conservation of mass? Yes, we probably are right now because, again, it's just a skeleton. In the subsequent videos, we're going to learn how to balance, and we'll balance in order to re-obey, if you will, the law of conservation of mass. Now, if you'll go to the next page, I've got some practice for you. 7 through 10, I want you to write these skeleton equations. Hit pause and do so. And then when you've got them, hit play again, and I'll have the answers posted so you can check your work. All right, let's see how well you did. Number 7, all I want to point out is that we do have a diatomic gas, and this is the case where you would add the triangle or the word heat. In number 8, we had a catalyst. So hopefully you have something like very similar to what I have written here. Let me just point out the state of matter for the H2O2. If you just had written there liquid, you would also be fine. Hydrogen peroxide is typically a solution. You buy it in those brown bottles from the drugstore. That's a water solution, but that's not a big deal. Number 9 is a precipitation reaction. So you had to figure out that PbCl2 was a solid, so that was important for that one. And then lastly, number 10, I could have given you a little bit better instruction here, looking back on it. This has to be in solution, so I probably could have, should have put the word solution of copper 2 sulfate there. So if you didn't get the correct state of matter on that one, you put solid, and then both of your products will be solid, I would probably let you get away with that. Even though we're going to learn more about this type of reaction. It's something called a single replacement. It has to be aqueous. But if you didn't know that now, that's cool. We'll learn it as we go. Otherwise, if you have any questions about skeleton equations, see me, and we'll do some reviewing one-on-one.